Hello everyone. Thank you for joining us. In today's webinar, we will discuss about micro-electromechanical systems, or commonly referred as MEMS. MEMS technology is used in various kinds of applications including accelerometers, magnetometers, barometers, optical switching technology, microscale energy harvesting, ultrasound transducers, etc. Multiphysics simulation is quite often used to study different designs of MEMS devices. Today, using one of our flagship products, EMS for SOLIDWORKS, we will show multiple MEMS applications. Before discussing today's agenda, let me introduce us. My name is Cal, and I handle sales and marketing division of our company. My colleague Majdi El Fahem is working as an application and technical support engineer in EMWorks. He will be delivering the technical part of today's webinar. Before moving on, I would like to highlight few points. During this course of presentation, if you have any questions, please feel free to use the chat window to type in your questions. We will answer them at the end of this technical presentation or will reply to you via emails. A webinar recording link will be sent to all the registrants in few days. Our agenda for today is following. I will briefly talk about our company EMWorks, where we are located and what products we offer. Then my colleague Majdi will present the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMWorks for its software users. EMWorks offers 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of computational electromagnetics. In addition, our products are gold certified by Dassault Systèmes SolidWorks Corporation since the year 2008. As you can see on the screen, we have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Schweinfurt, Germany. Now let us take a quick overview on EMWorks products. We offer 4 products with various add-ons covering a wide frequency range. Our first product is called EMS, which is used for electric and magnetic field modeling for low frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, MEMS devices, actuators, circuit breakers, transformers, and electrical machines. Our second product is called HFWorks, which is used for electromagnetic simulation of RF, microwave, high frequency and high speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, and waveguides. Our third product is called EMWorks 2D, which currently offers 2D static analysis and covers simulation of planar and axisymmetric geometries. Our fourth product is called Motor Wizard, which is a template-based motor design software. It currently offers analytical and finite element analysis of brushless DC motors. In addition to these software solutions, we offer few multiphysics add-ons which can be used with these products like thermal, motion, linear statics, and circuits. In today's webinar, Majdi will utilize EMS product to study and demonstrate different MEMS applications. Let us briefly touch upon the licensing structure offered by EMWorks. We offer 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual license, while in the rest of the 2 programs, our licensing structure is usually annual based. I would now request my colleague Majdi to take over and present the next part of this presentation. Thank you.
Thank you, Carl. Hello, dear attendees, and thank you all for joining us in today's webinar. In this session, we will cover the topic of micro-electromechanical systems and see how EMS for SolidWorks can help to study and design different MEMS devices. In this demonstration, we are gonna present to you our solution inside SolidWorks to design and analyze wide range of MEMS applications. We will start our presentation by an overview about MEMS devices. Then we will have a look on the main design challenges posed by MEMS applications versus some of our proposed solutions. After that, we will go over a couple of MEMS applications solved with EMS through screenshots and live demonstrations inside SolidWorks. At the end, with a conclusion about what we have seen, we will finish our presentation. As you already know, micro-electromechanical systems help to reduce the size of complex engineering devices to a micrometer scale. They are much smaller, cost less, and consume less power than earlier methods of implementing the same functions. They are also highly sensitive and extremely accurate. MEMS devices, which can vary from relatively simple structures with no moving elements to complex electromechanical systems with multiple moving elements, are capable of either creating an electrical signal due to the change of physical property or generating physical effect or movement when subjected to electrical signal. These devices have traditionally been referred to as sensors and actuators. As shown in the top right figure, MEMS application can be roughly categorized into several distinct fields, including inertia sensing, one of the most dominant fields of the past few years, optical transmitting, pressure sensing, biological and medical implementation, radio frequency utilization, and the newly developed energy-related field. Aside from these MEMS application fields, their specific device market forecasts were shown in bottom left figure. It can be concluded that MEMS devices used in industrial and consumer fields will continue to have a steady growth in the next few years. Specifically, huge progress and a sharp market share increase can also be observed on devices used in medical applications in the near future. This expansion in demands requires an increased effort on the other side to design, qualify, and manufacture MEMS products. To meet the high demand on MEMS devices and cover more fields of applications, systems designers use CAD design and simulation tools to build and develop more innovative and efficient products in a less time with a less efforts. They can help to study these tools. They can help to study more design iterations and reduce time to market the new products. Prototyping costs can be reduced as well. In this context, we propose to you our solution, which is EMS for SolidWorks, to analyze and create innovative MEMS products. Since we will go through it later during our demonstrations, briefly, EMS is a 3D electromagnetic solution with a few multiphysics options, and it is fully embedded inside SolidWorks. While studying a MEMS device, there are a couple of challenges that can appear to designers. Our suggested solution, which is EMS for SolidWorks, can help to tackle and overcome these issues. Now let's have a look on some challenges posed by MEMS applications. First, as we mentioned earlier, MEMS applications can be in the scale of micrometer and can have complex structure which need a robust and flexible CAD solution like SolidWorks. SolidWorks has an intuitive workflow and several features allowing an easy geometrical manipulation. Also, designers investigate the use of different materials options versus the output results to get the right and the optimal behavior of their devices. This includes different material types, anisotropic materials, temperature-dependent materials. For this reason, EMS comes with a rich and well-organized material library offering the possibility to apply different material categories. Ohmic losses, electric and magnetic forces, circuit parameters including capacitance, inductance, resistance are important parameters that determine the function of the device. EMS allows both electric and magnetic simulations which compute all these results under static, harmonic, and transient conditions. MEMS applications address multiple physics like electrical, thermal, and structural fields and may require the coupling between them. For example, micro-actuators involves electric conduction, thermal, and structural fields. In this regard, EMS provides a flexible and a single platform allowing an easy coupling between the different physics without any limitations. Moreover, these couplings, which are performed within the same study, help to avoid the issues that may come from importing and exporting data like meshing issues and geometry losses. Design or increasing the design iterations helps to improve and optimize the final product. Using EMS parametric studies and SolidWorks multi-configurations both help to cover more simulation scenarios in a reduced time. Globally, these are the main key designs of MEMS applications. In the remaining presentation, we are gonna see few MEMS examples and see how EMS for SolidWorks can be used to study and analyze these examples. But before this, we will have a quick look into EMS environment. As we can see now, we have a MEMS micro gripper actuators. It is created with SolidWorks CAD tool. Let's go to EMS tab. EMS, as we said, it is fully embedded inside SolidWorks. Let's create new study, right click, go to study. In this page, we can see 6 modules. They cover magnetic and electrical simulations. We can find magnetostatic, AC magnetic, and the transient magnetic for magnetic simulations, and electrostatic, electric conduction, and AC electric for electric simulations. We have the option of parameterization. This feature allows to parameterize both geometrical and simulation variables like dimensions, distances, current, number of turns, voltages, and materials properties. Let's go to coupling analysis tab. In this page, we can see thermal coupling, structural coupling, and also we can couple our magnetic or electric studies to SolidWorks motion. This by this option. Let's go back to the main page. Okay. Let's choose thermal, structural. And for thermal, also as you can see, we can have steady state or transient simulation. Let's stick to steady state for now and create a new study. After creating a new study, an EMS, what's called EMS tree, is generated. At the top, we can find the material list. We can apply a material using this option, and we can see EMS material library. It contains the default material, and we can also add or customize our own materials. Like here, there is a new lab material, we can create or add any material. Okay, under the materials list, we can find the electromagnetic inputs, where we define electric or magnetic inputs. Also, we have thermal inputs like this. We can define temperature, convection, and so on. And we have the structural inputs. It contains constraints, loads, and connectors. So as you can see, thermal, and structural fields are coupled within the same study inside EMS for SolidWorks. So no need to export or import any data. We use the same mesh for all the simulation types. So this is EMS measure. You just right click to create default mesh. These are some options. You can play with them to improve your mesh or make it coarse or fine depending on your needs. We have this option also to apply mesh controls, where we need also to make the mesh finer or coarser depending in our simulations results. Okay, let's go back now to our presentation. Now we are back to see a couple of MEMS devices and how EMS is used to solve these examples. As you can see, our first example is a comp drive actuators. The electrostatic comp finger drive has become an integral design for microsensor and microactuator applications because they feature an easy design, fabrication, and implementation. They are used in different applications such as optical communication, biomedical engineering, wireless communication, and nanotechnology. The actuator consists of two interdigitated structures. One is fixed and the other is connected to a compliant suspension. The moving part consists of 4 fingers, whereas the fixed one is formed by 5 fingers. The driven voltage between the comp structures causes the displacement of the movable fingers towards the fixed fingers by an attractive electrostatic force. The displacement can be measured using the equation shown in the bottom right side. Increase in traveling distance and force output are two major concerns in developing comp drive actuators. EMS electrostructural analysis aims at finding the resultant deflection of the moving fingers under an applied DC voltage. Gravity is neglected in this study. After running an electrostructural study inside EMS, we obtain electric and mechanical stresses results. So here we can see the electric potential and the electric field results of the simulated example. The maximum voltage is 130 volt. It is our applied voltage, and the maximum electric field is on the air between both fingers sets. In this slide, we can see both mechanical displacement and stresses. When 10 volt is applied, the maximum displacement is obtained on the last finger of the deformed structure, which is around 4.8 exponential minus 3 micrometer, while the maximum stresses are reached next to the fixed anchor. Animations of both displacement and stresses results are illustrated in the following figures. This kind of animations are automatically generated by the software. As we mentioned earlier, one of the main concerns in developing comp drivers is increasing the traveled distance. For this reason, we varied the applied voltage while the displacement and von Mises stresses are measured. We can see that both quantities increase with the voltage from 4.8 exponential minus 3 micrometer at 10 volt to 0.9 micrometer at 130 volt. In the same context, to increase further the displacement of the actuator, different modified structures are analyzed. As can be seen, the first configuration called fixed beam, which is already simulated. Now we are gonna see the results of the both second configuration, which are the crab leg flexure beam and the folded flexure beam structures. We talked at the beginning about SOLIDWORKS multi-configurations. This feature allows to have different configurations and geometries within the same model. And this is what we have done, or what we are doing for these kind of simulations. This also gives more flexibility to our work and facilitates comparing different design results. Here we can see the mechanical displacement and the stresses results for the second configuration. The displacement is around 6.6 exponential minus 3 micrometer for these configurations. Let's move to the next. In this slide, the results of the folded flexure beam are shown. Same behavior can be noticed but different values. The displacement is around 9.4 exponential minus 3 micrometer. In the next slide, we're gonna see the full picture of these simulations. So the results of the three configurations simulation are collected and superimposed in the following figures. However, it can be envisaged that for all structures, the displacement of the moving set finger increases with the voltage, but it has not the same rates. We can see that the folded flexure beam design allows a maximum displacement up to 1.6 micrometer compared to the other designs, where the maximum displacements are respectively 1.2 micrometer and 0.8 micrometer for the crab leg flexure beam and the fixed beam. One more factor that has a great impact on the displacement is the electrostatic force. Once this force which is created between both finger sets, increases, the displacement increases as well. We can notice from the left figure that the electrostatic force rises with the applied voltages. These displacements are determined by measuring the capacitance of the deformed structures. When the displacement increases, the distance between the actuator finger sets decreases, and therefore the actuator capacitance decreases as well. This can be seen from the right figure. The capacitance decreases with the displacement. As a conclusion, the resultant displacement of such MEMS application can be improved by increasing the supplied voltage and or optimizing the flexure design. More factors can be studied, like the flexure length, the material type, etc. Now we're gonna see inside EMS how to define such a problem and how to use multiple configuration to compare results. Okay, so in front of us we can see the first configuration of our simulated comp drive actuators. Let's go to EMS assembly and right click, go to study. Here the simulation is based on electrostatic force, so we need to use the electrostatic module. Select electrostatic, go to the coupling analysis, select structural and validate. A new EMS tree is created. As we said earlier, we start by applying the materials. Apply material to the outer region, air to the outer region, and these fingers are made of polysilicon. So we can find this in the recent applied material since we used it in my previous simulation. These are my already solved simulations. Okay, let me show you how to apply or how to define a new material. We can go to the material browser from the top level. Okay, this is a user, we can add a new user library 2, for example. A new library is created. We can create another subfolder or directly create a new material. Add a material, let's call it test material. Okay, then you will have all the needed properties for a material. So we have conductivity, electric conductivity, permeability, permittivity. We have also thermal properties and structural or mechanical properties. And we have isotropic, orthotropic, temperature depending properties. We can also have a lossy, like here we have a lossy material. We can apply a lossy material and so on. Let's close this and go back to our simulations. Close. Okay. Okay, we continue by applying the electromagnetic inputs. Right click here, we define fixed voltage, we select the fixed finger set, it is fixed, this is not moving, and say 0, it is 0. Another fixed voltage, it is applied only on the anchors here. So we should select this body only. Okay, we can use this filter in SolidWorks. Okay, we select this body and say and input the voltage. It is 130 volt. Validate. Okay, let's define our structural constraint. This is fixed, and we fix this surface from this anchor. Okay. This is basically what we need to do for all the simulations. So are the main steps. Apply material, apply electromagnetic inputs, structural or thermal inputs. If needed, then create mesh or directly run your simulation. So, okay, let's check our simulation, already solved simulations. This is my simulations results. Let's have a look here. Electric field. You can see our electric field. We can plot vector. So this is the vector plot of the electric field. Here is this 0 because we applied the fixed voltage there. There is no electric field there. And here is the maximum electric field. Okay, let's check the displacement. This is an amplified displacement, so let's modify this factor. To make visible this deformation, we can amplify. So we use this is a default scale, and here is the true scale. We cannot see any displacement using the true scale because the displacement is too small. And here is the defined. Let's use our defined scale. Let's multiply this by 10, for example. Yeah, we can see small displacement there. Can switch the unit. Okay, 0.8 micrometer. Okay, now as we said earlier, we use the multi-configuration to check or to run different configuration of these comb drive actuators. Let's check SolidWorks. We have our 3 configuration: fixed beam, folded beam, and the crab leg flexure beam. So we can switch between them whenever we want. So let's move to the second. Right click here, activate the configurations, and you can see it changed. The configuration changed, the model changed. Okay, let's check the results. I have already solved this study also. You can see the displacement is 1.11 micrometer. And let's move to the last configuration. Activate configuration. Okay, it is active. Let's check the displacement. Okay, as you can see the results of the last configuration. Okay, I show you the model. Here is the last configuration structure. It is folded flexure beam. So this can be made within the same model inside SolidWorks. We use the multi configuration and EMS can handle different or several configurations at the same time. Okay, let's continue our presentation. Now get back again to our presentation to go through our second example. It consists of a microthermal actuator that converts thermal energy into force and motion. Here we study a low voltage microthermal actuator that develops relatively large to medium thermally induced deflections. The working principle consists of applying an electrical signal which generates a current in the different arms of the actuator. This current will or heats up the actuator, which will lead to the deformation of the arms because of the thermal stresses. The deformation rates and direction depend on several factors like the way we excite the actuator, how much voltage is applied, and so on. The following table shows the main properties of silicon used for the studied actuator. These properties are supposed temperature independent at this stage. A DC voltage is applied into our simulated actuator. It generates a big current density at the hot arms, the thinner ones, as can be seen from the right figure. The current density flowing through its arms heats up the actuator. We can see that the steady state temperature is reached after 2 milliseconds and the maximum temperature is located in the extreme hot arm. This is unexpected behavior because we have seen that the maximum current density is in both hot arms, but since the middle hot arm is closer to the cold arm, the thicker one, it gets a bit lower temperature than the second hot arm. The extreme right figures show the temperature variation across the actuator from cold to hottest arm and along the hottest arm. The Joule heating caused by the current generates a structural deformation in the actuator. We can observe that these thermal stresses cause about 3 micrometer displacement in the structure. By varying the applied voltage, we get the following results of the temperature and mechanical stresses. Both maximum temperature and displacement increase with the applied voltage because the actuator resistance doesn't change, and by increasing the voltage, more current will flow in the actuator. Continuing with the same example, but now we are using temperature dependent material properties. Continuing with the same example, but now we are using temperature dependent material properties of the silicon. This can give more realistic results. EMS allows to define such properties using its curve function. You can import these data from text or Excel file as well. We can see from these results that by using temperature dependent properties, we got higher temperature plus bigger displacement compared to constant properties. But the difference in results is still acceptable if we choose to use constant properties for the simplicity of the problem. Now, using a simpler actuator, we are going to investigate the impact of a few geometrical parameters on the results. A series of simulations is performed using parametric analysis of EMS. After running a couple of parametric studies using EMS, we get the following results. The left figure shows both temperature and displacement versus hot arm thickness. By increasing the thickness of the hot arm, its resistance decreases and therefore the temperature drops down. Since temperature decreases, the displacement decreases as well. Concerning the middle figure, the cold arm thickness is varied. However, we can see that the maximum temperature is almost constant, and this is normal since the maximum temperature is in the hot arm, but the displacement increases with the cold arm thickness. This is due to the extra weight of the cold arm. The third figure gives the results versus spacing between cold and hot arms. The temperature is constant while the displacement is decreasing versus the spacing. Now we arrive to our last example, which is valveless micropump. Micropumps are one of the essential MEMS components for the microfluidic system and have a significant potential in chemical control of nanoliter flows for drug delivery as well as chemical analysis and mixing. Micropumps based on electromagnetic actuation are the common integrated devices that have been applied to the needs of biomedical actuation applications. These micropumps gave rise to a new emerging microfluidic field requiring a compact method of actuation to produce the needed flow. One of the commonly used micropumps is the valveless actuated one. It comprises an electroplated permanent magnet mounted on a flexible PDMS membrane and a base glass substrate holding a fixed microcoil. Such type of micropumps allows to create a significant driven flow pressure. In the pumping operation, fluid is driven through the pump by applying a current to the microcoil such that an electromagnetic force is established between the coil and the magnet, causing a resulting deflection of the PDMS diaphragm. The PDMS is specially chosen as the membrane material since it has a good flexibility characteristic. Consequently, the large diaphragm deflection allows the rate to be easily controlled under low electrical current and frequency. The left figure shows the variation of the resultant magnetic force versus the applied current from 0.4 amp to 1 amp. A good coherence is observed between the reference results and those obtained by our tool, which is EMS for SOLIDWORKS. Under the effect of the magnetic force acting on it, the PDMS diaphragm is bending upwards. It attains a maximum deflection of 15 micrometer under 16.9 micronewton force, corresponding to a current input of 0.9 amp as shown in the middle figure. The right figure contains a comparison between experimental, analytical, and EMS results. It shows the membrane deflection versus the generated magnetic force. It confirms also a good agreement between the different results and the ability of EMS to estimate the magnetomechanistic behavior of a micropump actuation under low current. Finally, we come to the conclusion of our presentation. To summarize, EMS was used to study different MEMS devices, including electric and magnetic applications. Electrostatic and magnetic forces were computed by EMS. Ohmic losses and capacitance results were calculated by the software. The temperature variation and the displacement results were estimated versus different situations and scenarios. And finally, EMS results were compared to experimental and analytical results, and they showed a good agreement. Thank you for your attention and time, and I hand over again the screen to my colleague Carl to continue the presentation.
Thank you, Majdi. We used EMS product to study different designs of MEMS devices. Let us take a quick overview on EMS software. EMS product offers electrical and magnetic solvers. In addition, few multiphysics options are available with this product, like thermal, motion, linear statics, and circuits. EMS software is available in 4 packages: electric, magnetic, professional, and premium. To get more information on the software packaging and pricing, you can connect with me after this webinar. Now let us do a quick recap on EMWorks products and their related applications. We can divide EMWorks offerings into 2 categories: applications related to low-frequency simulation and applications related to high-frequency simulation. Within low-frequency category, we offer 3 products: EMS 3D, EMWorks 2D, and Motor Wizard. These products can be used to design and simulate applications such as cables, insulators, bus bars, solenoids, magnet arrays, eddy current braking systems, wireless charging devices, transformers, and electrical machines. Within high frequency category, we offer one product known as HF-Works. This product can be used to design and simulate high frequency applications like antennas, waveguides, filters, resonators, and connectors. EMWorks offers various free learning resources. With the software purchase or an evaluation license, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all the users of EMWorks software. I encourage everyone to try our software and experience its capabilities. Upon trial request and user qualification, we offer 2 weeks of free access to the limited version of the software. In this limited version, users can access many predefined model examples and tutorials to learn about the software features and capabilities. To request for a trial license, visit our webpage, go to our Contact Us page, fill in your information, and submit your request. One of our representatives will reach out to you soon. I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you.